Okay, so today we are going to see some selected questions on work, power, energy and previous chapters which we have already covered. And by the way, also there are already recorded classes on work, power, energy in the short-term course EduMind 24. We can already have recorded. That is screen recorded classes. You can also watch that. Okay, I will share the links also that you will find in that STM JM24 playlist. Okay, so let us take one question. Looks like a good question. A body of mass m is slowly hauled up a rough hill. So there is a rough hill like this. This is a hill, and this length of this hill is L, and the height of the hill is H. And this surface is a rough surface. On this surface, a body, if some block is there, it is being moved. It is being moved by applying a force. Block has a mass m, right? So a body of mass m, okay, so there is a block, a body of mass m is slowly hauled, slowly slowly moved. So this block is slowly moved over this, okay, slowly moved up the hill by force. This force is tangential. Tangential means this is always parallel to the tangent. Tangential. This force is always acting tangential. This force is tangential. Tangential. Okay. Find the work performed by the force if the hill is height h, length of base is L, friction coefficient of friction is mu. Okay. So we need to calculate work done by this force. And block is going from bottom to the top of the hill. Okay, what is work done? If body is moved along alternative path, suppose if body is moved along alternative path means some different path, but it is going from the same point to the same point. Starting point is same, final point is same, right? So this force is always tangential to the path. So if the path is a different, then what will be the work done? First question is, what is the work done if it is moved uh, along this path? It is moving along this path. So what is this path? This is the path. Some path is there, and this force is acting along the tangent of this path. Okay. So first you calculate work done along this path due to this force, and then you choose other paths. Then you calculate work done along that path. So that is the question. Are you clear about the question? All of you are clear about this question? Yes. Okay. So this is a mountain or this is a hill. Okay. And this hill is starting from here, and this hill is going like this way. This is the hill. This is the surface of the hill. And this surface of the hill is a rough surface. And a block we are trying to move over this. There is a block. This block we are trying to move over this surface from the bottom. We are taking from the bottom and slowly moving means we are not giving any kinetic energy. And always you are moving. How are you moving? You are applying a force which is tangent to the path. Always the force is tangent. Velocity is zero now. Slowly means zero. Zero it is. Very slowly it is moved. So it is almost at rest. We are not giving any speed to this. Okay. There is no speed on this. And the force which is acting very slowly means that's what it is. Very slowly. Very slowly means very small speed is this. Its velocity will be there, but means you can say it's negligible. Negligible. You don't consider any velocity, but very slow it is. You can take a speed, but the speed is 0.0001 meter per second. Very small speed it is. Hmm. By a force which is acting tangentially. So this force is tangential. They are not saying anything about this force now. You have to think it is, but only thing is told that this force which is acting is always tangent to this path. Suppose, suppose for example, the block is here. Let us say block comes here at any place, other place it comes. Suppose block comes here. Now the force is acting tangential. That means the force will be like this. Force is parallel to the surface. That is what is tangential means. Okay, and we do not know its magnitude. Its magnitude may be changing, and of course direction is changing because the path is a curved path, right? So tangent of the slope is changing. So this force is always tangential to the path. Of course magnitude may also change because you need to keep it constant, speed. That speed is zero speed, you can say. So almost zero speed. You are dragging slowly. You are dragging it over the surface. Okay, that's the question. Hmm. Hmm. Whatever time it is taking, it may take last time. But time we don't have to calculate. We have to calculate work done. Okay. So we have to calculate work done by this force in taking the body from the bottom to the top. Length of this is L and height is H. That is first part of the question. What is the work done by this force? Second part is that if the path is different path, suppose if the path is dotted some different path, but still the initial point and final point is same, then what will be the same calculation? What will be the work done? Again same. No, this hill is, it is going over the surface, but the surface is a different surface now. It is a different hill. That's all. The hill now, the shape of the hill is different. Here this is a different shape of the. It is contact with the surface. Hmm. It is moving slowly. Slowly, it is moving over the hill. It is balanced. That is the meaning of that. That means it is always balanced. That you can say that. You are moving it, but you are keeping always in equilibrium. That is the idea. You are not accelerating it. You are not producing a net force. Because if you produce a net force, there will be acceleration. And if there is acceleration, speed will increase. So that means you are going it by keeping it in equilibrium. Always it is in equilibrium. Okay? Equilibrium means what? You understand now what is it? That's what it is. It is balanced. It is balanced. Hmm. No. The body can have acceleration zero, net force zero, but still it can be in motion. Newton's first law, you forgot? Newton's first law says that a body can be in equilibrium means net force zero means acceleration zero means either rest or uniform motion. So this body can be moving either in rest or in uniform motion you take, but very small speed it is. That is what it is. Okay. Then how will you solve this? So you study at any point of this motion. Suppose the block is at any point here, block is there. And let us say that this path is some curved path, we do not know. Some path is curved. We do not know what kind of curve it is, what curve it is. Okay. Now let us say right now it is contacting here. What are the forces acting on this body? Draw the free body diagram. Mg, and here a normal force also will be acting at this contact. That I am showing it like this way, okay, along the normal. I am showing it like this, normal Mg, and the force which you have applied, friction force, which is parallel to the surface, sorry, the applied force which is parallel to the surface, and friction is also parallel and it must be acting opposite, tangential, opposite it is acting. That's the friction force. Clear? These are the forces acting. Now suppose if I draw this tangent, because this is a tangent here, this surface. Suppose this angle is theta. So at that instant, this angle also will be theta. I know all this and I can resolve this, right? So at this instant, I am resolving mg, this mg cos theta, and this side will be mg sin theta. And it is in equilibrium means I can keep in equilibrium. So normal should balance mg cos theta and this force friction plus mg sin theta, right? And friction can be written as mu times normal. Yes. No, no. What are we calculating? We are calculating work done by that force. Normal is zero. That is always zero because normal always acts perpendicular to this. So we want to calculate work done by that force. Okay. So first of all, to calculate the work done, we know the formula for, and this force can be a variable force because direction is changing, magnitude may also change. So work done will be integration of this force dot dr, right? That's what it is, force dot dr. And one thing is very important to note that the dr, which is the displacement, and this force are always in the same direction because force is always tangential to the path, right? So that means angle between them is 0. So I can write f dr cos 0 degree, right? So then I can write this as f dr cos 0 is 1. So capital F we can substitute from here because it is balancing, but we also know that friction is mu times normal. That also we know. Remember that law of friction. So this is mu times normal because body is sliding. So this is like kinetic friction, mu times normal, mg sin theta. And normal I will substitute as mg cos theta plus mg sin theta. Mg we can take comma, mg we can take comma. So mu cos theta plus sin theta. Note that theta is only changing here in this, correct? Theta will be changing because the slope of this path is changing. Okay, so let us try to substitute mg mu cos theta plus sin theta into dr. Okay, so now this constant mg I will take out of integration. Then we will left with mu cos theta plus sin theta dr. Okay. Now let us break this integration into two parts. Mg is anyway outside. Let us break this integration. First time we will take mu cos theta into dr and next sin theta into dr. Now, how to solve this? How is cos theta dr? This is a very important concept now. So this path which we have taken here, this path which we have taken here, small path we are taking dr. This small path dr which we have taken, this dr or this line is making angle theta with the horizontal, right? So this is also making the same angle theta, but this dr theta we can resolve as this dr cos theta and this dr sin theta, yes, which is nothing but dx and dy. This is like dx and dy. So dr cos theta is dx and dr sin theta is dy. So that's what we are going to write it here. So mu is anyway constant comes out. Dr cos theta we will write as dx and dr sin theta we will write as dy, integration of that. So now you see this integration has become very easy, and we know this dx integration is delta x, change along x-axis, and this dy integration is delta y, change along y-axis. And we already know what is the changes happening, initial and final total changes. So total change along x-axis is L and total change along y-axis is H. So this is what is delta x and this is what is delta y. Okay. So now without doing much we got the idea, mu into L plus H. This is the work done by this force. Yes, work done by this force is given as mg L plus H. Now see, it doesn't depend on the path because integration of dx is delta x. Delta x is same. If you go through a different path, it doesn't matter. You may go different path, but change along this x-axis is same because initial position, final position is same. So change along that delta x is same as L and change along delta y is same as H because initial and final positions are same, right? So that is the key idea of that. That means the work done is independent of the path. Work done is independent of the path. Then understood this calculation? That's a good question. Hmm. Next, let us go to the next question. Speed is zero or speed is very slow, constant speed, right? It is always in equilibrium. That is the key idea. It is not being accelerated. Okay. Okay, now take a very good question. There is a block of mass m. It's kept on a wedge. A block of mass 10 kg is released. This mass is 10 kg. 10 kg is released from the top of a smooth inclined plane. This is a smooth surface, a smooth inclined plane, wedge which is moving horizontally towards right. So this wedge is moving horizontally in this direction. This wedge is moving horizontally with some speed, which is given as u. This is 10 meters per second. Okay. Inclination of wedge, this angle theta is 37 degrees. They have given it. Calculate work done by the force applied by the wedge on the block in 2 seconds. Calculate or find work done by the force applied by the wedge on the block in 2 seconds 2 seconds in a reference frame, reference frame, reference frame attached to first the ground and second the patch. Again, I will read the question, what the question is saying. A block of mass 10 kg is released from top of a smooth inclined surface of wedge which is moving horizontally towards right at a constant speed of 10 meters per second. Inclination of wedge is 37 degree. Calculate work done by the force applied by the wedge on the block in 2 seconds in a reference frame attached to ground and wedge. So there are two questions in this. Okay. So first you have to understand what the question is. Are you clear about the question first? I will again explain the question. First, understand what the question is saying. The question is saying that there is a wedge which is moving with a constant speed, 10 meters per second. Okay, and there is a block which is released on that wedge. It is released. So as soon as it is released, and note that the surface is a smooth surface. They are not talking about this surface, anything about that. That surface may be tough, smooth, doesn't matter because it is going with a constant speed. Okay, and this surface is smooth and this block was released on this. So there will be interaction force between the block and the wedge. Correct? There will be interaction force. Normal force. Yeah, normal only is the interaction because friction is not there. Right, normal only the interaction force. So that means they are asking calculate work done by force applied by the wedge on the block. So wedge will apply only normal, right? Normal force only. So the normal. So they are asking the work done by the normal force. Okay. So normal force, how much work is doing on the block? That is the question in 2 seconds. In 2 seconds, but that normal force is studied or the force of interaction is studied from two different frame of reference. One frame of reference is the ground and another frame of reference is this wedge itself. That means observer are at two different places. One time, first part of the question, observer is on the ground, and second part, the question, observer is on this wedge. Okay, so according to both the observer, what is the work done on this block due to the interaction force between the wedge and this block, right? That is the question, and time is given in 2 seconds. In 2 seconds, what is the work done? Clear? Are you clear about the question? So, how will you take the approach? 50 Newton. Let's try, and value of G you can take as 10. Okay, they are also saying value of G you take as 10. So first of all, we have to draw the free body diagram. Free body diagram we have to draw. So draw the free body diagram. Note that the free body diagram drawn in this body from two frame of reference can be different if this frame is under acceleration. So tell me, is that wedge under acceleration or not? not under acceleration. Okay, so that means from both these places we should give the same answer. Let us try that. Of course, the forces are not going to be different. Normal calculations you can do from this framework because pseudo forces are not going to act, right? Pseudo forces will act only when there is the acceleration, frame has acceleration. So, anyway, let us first try to draw free body diagram on this water. So, forces acting will be mg and forces acting is normal, which will be this way, normal, and normal is acting like this. This angle is already theta, they have one. Even so, if this what is happening to the, that means I want to calculate normal. How do we calculate normal? Why? No, 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 no. See, that I think that is where you are mistaken. See, it is not given that the body block is moving together with the inclined plane. The block can slide on the inclined plane, but block is just released on that plane. So there can be relative motion. That means block can slide over the plane also. Not jump. So you can say that normal will balance mg cos theta. Can we say that? So for that you need to see the motion with respect to this frame of reference. Okay, you need to study from this frame of reference. That means relative to this surface it can only slide down. So relative to this surface first. So first you have to study from the observer on the wedge, right? Because with respect to the wedge when you are studying, then only you can say that with respect to wedge it is going down only. That means, suppose if you are studying with respect to weight means it can only slide down. Then you can see with respect to weight it can go only in this direction. So you are the observer now on the wedge, and now you are trying to resolve forces. So resolve the forces. This theta. So this is mg cos theta, and this is mg sin theta. So with respect to this you are releasing it, right? So you are releasing it means speed will be 0, and normal has to balance mg cos theta. Normal has to balance mg cos theta. So relative to this reference frame, this body has to go only downward because downward acceleration will be g sin theta. You already know this, right? Yes, because anyway surface is smooth, so only acceleration related to this is g sin theta, because mg sin theta is the net force, unbalanced force, which is mass into relative acceleration. So g sin theta is nothing but the relative acceleration with respect to this frame of reference, right? So now this observer can measure in 2 seconds how much it will go. It will go some distance, but the problem is that the normal mg cos theta is constant. Mg cos theta is constant, right? And what he will see, that he will see, this observer will see this body going down. So this displacement, let us say it has some displacement delta r, let us say some delta r displacement happens, we can calculate that, but the force normal is perpendicular to this displacement. Yes, because body is displacing in this direction, right? And this normal is perpendicular to this displacement. So then we don't have to calculate 1 because we know 0. Yes, yes. For the second case we are telling. Okay. So work done by this force from wedge. Okay. From wedge means observer is on the wedge. So second part we are taking from wedge when you take this work done will be 0 because normal dot displacement is going to give us 0. That is the second part answer. But first part answer, normal will remain same. Remember that normal, because if you see from ground or if you see from that frame, there is no pseudo forces. So normal will be same mg cos theta only. But the displacement from ground, the observer who is seeing from the ground, the displacement of the body will not be in the same direction, because that displacement is happening relative to that wedge. Now you think about it. Observer from the ground, what is the displacement for that observer? Why parabola? But it is not free fall now. Both are changing, it's okay. But parabola is when in one direction there is the acceleration, another direction constant velocity. So observer from the ground, what does he see? He is seeing the wedge moving, and on top of wedge, this block is sliding. So first case that we have done here, first let us try to think about this. Observer is seeing this block going down with the acceleration of g sine theta, right? And it was released from speed 0. So how much displacement it will have? Let us calculate that displacement delta r first. Ut plus half at square. Ut plus half at square. U is 0. Like this acceleration is g sine theta, which will calculate. G is tan sine of 37 degrees. 3 by 5, right? That means 6 meter per second square. So acceleration is 6 and time they have given 2 second, 2 square. 2 got cancelled, 6 into 2, 12 meters. Okay. So this observer which was on this frame, he will see that in 2 seconds this has gone down the plane 12 meter. But of course he has not seen any work done by normal. So according to this observer, there is no work done by normal, but it has got displacement 12 meters. Yes, in 2 seconds. Now I want to calculate displacement of this block. Let us say this is the block and this is the wedge. So I want to calculate displacement delta r for this block. This delta r factor for the block is displacement of block with respect to wedge plus displacement of the wedge. You remember relative velocity. If you remember relative velocity, then you will use this. That's what it is. Game is over now. So block displacement now you calculate. Block displacement you calculate. So block displacement is block with respect to wedge already we have calculated, that is 12 in that direction. Wedge is going horizontally, right? So you need to add these two vectors. You have to add these two vectors, but this normal force magnitude will be same. So what we need to do is, now see how do we reduce the calculation. Now with respect to the ground frame, we are calculating work done by normal. So normal is a constant force, we know that. So normal dot product of this displacement of the block we are going to do. So normal vector dot. Now this block displacement I will write as displacement of block with respect to wedge plus displacement vector of the wedge. Okay, now let us open that dot product. So n vector dot displacement of the block with respect to wedge plus normal vector dot displacement of the wedge. Now this vector is going to be 0, that already we know that, because normal on the block is acting perpendicular to the surface. and this displacement is parallel to the surface. That's why this is dot product we are calculating now. Work done is dot product of force and displacement. So we have to no, we have to calculate work done by normal force. You understand question? We have to calculate work done by normal force. First time when the observer is on the wedge, second time observer is on ground. Okay. So, so this calculation which we have done in the first part, work done by normal from observer on that frame. So that was from wedge. That is what we have calculated 0. This was for 0. But now this is from ground. This is from ground. So only changes is happening in the displacement. Okay, normal is the same force, but displacement there was relative displacement. That displacement was displacement of block relative to the wedge. That was this one. This part which you are seeing here when we are opening this part is 0 because this is work done in that first case. Okay, that is what. And second term, what is coming now? This is what we need to solve here. This is we need to solve. So how do we solve this? We need to know magnitude of normal already we know. We need to know the magnitude of displacement of wedge, and we also need to know the angle between them. Okay, so think about it. So this is the displacement of the wedge. Wedge is displacing because wedge is going with a constant speed, right? Wedge is going with a constant speed. So this distance is speed into time that we can clearly see. This wedge distance is speed into time. Speed is 10 meter, time is 2. So 20 meter will be its displacement. So its magnitude we know. Normal magnitude also I think we have calculated. What was normal? Mg cos theta, right? Normal was mg cos theta. So how much magnitude it was? That mass was given, na? How much mass was there? Log mass was how much? 10 kg, 10 kg, 10 kg was. Okay. 10 kg. Okay, so this force we calculate 10 into g is also 10 and cos of 37 degrees 4 by 5. Right? So from here 5 into 2, 10, 80 Newton it is. Okay. So we know the normal magnitude, but what is the angle between this normal and this wedge? Remember, this is the wedge direction and normal is like this way. This is normal. So what is the angle between this? Can you tell what is this angle? Because this is 90 degrees, this is 37 degrees, so this is 50 degrees. Yes, yes, correct. So this is what we are now going to open. So this normal magnitude, this magnitude of delta of the wedge into cos of 53 degrees. This will be the answer. Now solve it. So this is 80. Then this is wedge, this 20. Cos 53 is 3 by 5. 3 by 5. Okay. Now solve it. 5 into 4. 8 into 4. 960? 960 joules. Yes, this is the correct answer. Did you understand this? That's not easy question. It's a good quality question. Okay, any other doubts if you have, you can ask. Yes. First part, the first part is that this block you are studying with respect to this frame. Okay, this frame. The work done depends on force, displacement, and angle between them, right? You know that it is dot product. So here the normal force calculation is going to be same from both the frame of reference. Why? Because there is no acceleration happening, so no pseudo forces are there. So normal calculation will be same, but the displacement is not the same. Angle is also not the same, because from different frame of reference, displacement is different. Suppose you are inside a train and you are looking at an object inside the train which may be moving. Suppose you are playing with a ball inside the train. Because you are moving, that body displacement is different from your frame of reference and from ground frame of reference. So that displacements are different here. That is what happens here. So although the force is same, but now with respect to this observer, when studying with respect to this observer, when you draw the forces, this object can only slide over the surface. That is why you balance normal with mg cos theta, and this direction acceleration was g sin theta because there was no friction. So when you have released it, anyway normal is perpendicular to displacement, so work done here is 0, you know that. But you can calculate displacement because acceleration is g sin theta and you have released initial speed 0. So constant acceleration delta r ut plus half ut square you calculate. So from this frame of reference, this person will see that in 2 seconds it will go 12 meters. But ground person will not see the same thing. Ground person will see the same force, but he will see a different displacement and different direction of displacement. Okay, that is the main thing. So how the ground person will see? So this is the relative, I think relative velocity, relative motion you have already studied. So this equation is relative. So displacement of block is equal to displacement block with wedge plus displacement wedge. You remember rain man question, velocity of rain is equal to rain with respect to man plus velocity of man. Remember all those relative motion you have done. So same thing here. So now this block displacement you are calculating with respect to ground. This is the ground. Why we want now? Because now we are doing with respect to ground. So this is equal to block with respect to wedge plus displacement of wedge. So when you do this dot product, when you take first time this normal dot, this was block with respect to wedge, which was 0. Now second case, this is actual displacement of block with respect to ground, which is sum of these two displacements. So you are applying distributive law and you are opening the dot product. This is already 0, we know that. Now normal dot displacement of the wedge, that is what we want to calculate. Normal already we have calculated mg cos theta, and wedge displacement also we calculated because it is going at constant velocity. So displacement is speed into velocity into time, 10 into 2, 10 meter per second into 2 seconds, 20 meter. But its direction is this way. So this is horizontal direction, but force is acting normal to this surface. Force is acting normal to this surface. Normal to this surface. This is the force. So we want dot product of this normal and this displacement. This displacement is the displacement with respect to ground. This displacement. So we want to calculate this dot product of this normal and this. So normal is making angle 53 because this is 90, this is 37, this is 53. Okay. That's what is dot product we are doing. So normal into this magnitude into cos. Normal we already calculated. Wedge displacement we calculated. Angle we calculated. Clear? Anyone any doubt in this? Ask. Then okay, let us go next. A particle of mass 3 kg is there, and it takes 2 seconds to move from point A to point B under the action of gravity. Okay, and another. So on this body there are forces acting. What forces are acting? Mg is acting, and there is another force acting. No, there is another force given. Two forces are acting on this body. 12 y cap minus 3j cap. It is not in contact with any surface, so normal is not there. Okay. So So these are the forces. So two forces are only given, okay. So one is this force, applied external force, and this mg. Mass they have given as 3 kg. And they are saying that the body goes from point A to point B, okay, under the direction where they need to go. Okay. K cap is in the direction of upward vertical. See, they are saying that K cap is in the vertical direction. Okay, K cap is vertical direction. XY plane will be horizontal. That means, okay. Position vector B is B vector they have given. B vector position is given. That means position vector. That means RB vector they have given. 15 I cap minus 7 J cap minus 6 K cap. Velocity of the particle when it reaches B. So when particle reaches B, velocity is given as 12 I cap plus J cap minus 4 K cap. This they have given meter per second. See, everything is in SI unit. So first question is find velocity of particle when particle was at rest. So question, try to understand question. Question is saying that particle is moving from position A to position B. This position A position factor they have given. If you want, you can write XYZ component 15 minus 7 minus 6. Position of B they have not, oh, sorry, I think this is position of B only. This is position of B they have given. Position of B is 15 minus 7 minus 6. Okay. And on the body, two forces are acting. These and these forces are acting. What is going from A to B? Which path it is going, we do not know. But what is going from A to B? And velocity at B they have given. Velocity of at A they are asking velocity at A. Okay. That's the first part of the question. Then second part of the question they are asking is what is the position vector? Find RA. RA factor also they are asking. Position vector of A they are asking. Find work done by force at the particle. You have to also third part they are asking work done by this force in going from A to B. And fourth part of the question find change in gravitational potential energy. Okay, potential energy we have not discussed, that we will see afterwards. Okay, let us try this. Here you can apply work energy theorem. Work energy theorem I will give in detail afterwards, but note work energy theorem. Work energy theorem note here. I think work energy theorem will be used in many cases. Work energy theorem says that work done, net work done is change of kinetic energy. Very simple it is. Net work done change. Net work done means because on a body so many forces may act, right? Let us say on a body two forces are acting, F1, F2, F3, or three forces are acting. So this theorem says that the total work done, remember the total work done means work done by first force plus work done by second force plus work done by third force. Let us say three forces are acting. So work done by first plus work done by second plus work done by third is equal to total change of kinetic energy. Okay, that is a simple theorem, but it is a much powerful theorem. We can use this in this problem. So try this. Huh? Yes. We will discuss more detail and proof of this, but right now let us just use this. Okay. Work done, total work done. No, no, that we will derive it afterward. We have to just use it right now. Okay, the derivation of work energy theorem afterwards we have to do. But the theorem says that the work done by first force plus work done by second force plus work done by third force, sum of all the work done or the total work done is change of kinetic energy. Kinetic energy formula, I think you know that, right? Half mv square. So change of kinetic energy means half mv square final minus half mu square initial. Final kinetic energy minus initial kinetic energy. Yeah, yeah, yes. K2 minus K1 you can take. So how do we use this? So you know already it is given in this question. Everything is now easy because only two forces are acting, this and this, right? And mg, if you want to write force mg, you write mg force like this, okay? Because it's a vector, no? Let's write force mg vector as, because downward vector will be minus k cap, so you can write minus mg k cap. Yes, correct, right? Because mg is acting downwards, so direction is minus k cap. So mg into minus k cap means minus mg, and this force is given. So work done by this force plus work done by this force, that must be change of kinetic energy. And I think they have given speeds also. Speed they have, velocity they have given. So speed you can calculate, magnitude of this you can calculate, right? What is the magnitude of this speed? Can you tell? What is VB? Magnitude of this vector, root under 12 square plus 1 square plus 4 square. Add this 16 plus 17, 144. 144 plus 7. Root of 161. Okay. Root of 161. Okay. Meter per second. Okay. So let us apply this work energy theorem, because first part they are asking the velocity vector also they are asking. Okay, they are also asking velocity vector. So do you have any idea how to calculate? Anyway, we can calculate in, let us apply, let us not go by this theorem, let us think basic, because basic calculations we can do. We can add both the forces and we can find the net force. Once you find net force, you can calculate acceleration. Once you calculate acceleration, you can use the formula V equal to U plus AT. Done. That thing you can apply. Means constant acceleration will come, right? Because both the forces are constant forces, right? So both forces are constant, so the resultant force is also constant. And they have given position, initial position they have given, final position they have given, initial position we do not know, right? Okay, so first let us calculate net force and think about it. Okay, let us calculate net force here. Tell me what is the net force on the body. Net force is equal to, these two forces are there. One is the force, this applied force, another is mg. These are the only two forces. What is mg? G let us take as 10, I think. Let us take g as 10 to calculate easy. So mg value will be 30, right? 30. So let us write this. Huh. Which direction you want to resolve? No, no. See, to resolve, you should know the direction of acceleration. We do not know the direction of acceleration. That is why we will calculate net force is equal to mass into acceleration. So we can add, because forces are already given in two factors, right? We'll use vector equations. Because in inclined plane, we already know that it will go down, so we resolve. But here, we do not know, right? Yeah, directly we can add. Already components are given. Na ijk there components only. Okay. So 12 y cap minus 3j cap plus 21 k cap. and this is minus 30, so minus 30 k cap. So this becomes 12 y cap minus 3 j cap, 21 minus 30 minus 9, right? Minus 9 k cap. Okay, so this is the net force. Net force can be written as mass into acceleration. Mass is 3, so 3 into acceleration vector. So acceleration vector I can calculate 4 I cap minus j cap minus 3 k cap, right? So we got the acceleration vector. Yes, acceleration vector we know, and acceleration is constant. So we can think of using equations of motion. Vector equation we have to use v equal to u plus at, but time is not given. Think of other vector. Time is not given, so displacement is ut plus r. Again, time is not given. Then v square equal to u square plus 2x. V square means v dot v. Ah, yes. What? Hmm. No. Work done. We have to see the dot product of force and displacement, right? So, which force are you taking? Are you taking total force or individual? Because according to work energy theorem, we have to take individual forces. Work done by first force, work done by second force. So first, let us use kinematics. Now, basic kinematics we can use. Okay, v square equal to u square plus 2x we can use. So v dot v is equal to v square u dot u plus 2 a dot displacement delta r. Okay, so v dot v means v square. That means final velocity. We are going from A to B, so final velocity v dot v. That means magnitude of square of this. That means this become 161, right? U dot u square we do not know. We will think about it. That is what we have to calculate. U square means this initial velocity at A. 2 times uh, acceleration. Acceleration we have calculated, but what is the displacement? Hmm? Displacement we do not know. No. Why should we take all this thing? Displacement they have given na A and B, and they are also asking you to calculate. They are asking to calculate positions. So this is not origin. We cannot take. Displacement will be RB minus RA. RB they have given here, I think. Yes, RB. RA they have not given. Let us take RA as x comma y comma z. Right? X comma y comma z. So this displacement vector, A vector is here how much? 4I minus j minus 3k, and this displacement is final minus initial, so 15 minus x I cap, right? 15 minus x I cap plus displacement along y, so minus 7 minus y, that will become minus 7 minus y j cap plus displacement along k, so minus 6 minus z minus 6 minus z k cap. From here, we will not be able to solve because we do not know what is u here. We can get one equation, but think about it. Here you can get, when you open this, you may get something. So 2 times 4 into 15 minus x plus minus will become plus 1 into this will become 7 plus y, and this minus also will become plus 3 times 6 minus x. We cannot solve it because we do not know u, we do not know x, y, z, but this equation we are taking here. This equation we are taking here, right? Then what else we can do? We cannot solve. Work energy theorem can be used. Work done by first force and second force. Um, Displacement, we don't know. Initial kinetic energy. We don't know. Final kinetic energy we have here. We have here only final kinetic energy. What else can we do? No, no, they have they are asking that a vector also, second part of the question. They are asking the position vector of it. Only B factor is given. No, no, that is what they are asking. X, Y, Z means xi cap, yj cap, z cap. We have to find out. B they have given, position of B they have given. A position we need to calculate. We need to also calculate velocity at A. They have given position of B, velocity at B they have given, and the forces acting, two forces that they have given. Right? Mass is given. That's what is given. This force acting, this force, two forces acting they have given, and they have given the final position they have given. That's what they have given in the question. No, time is also not given. No, no, yes, yes, time is given. It takes 2 seconds to move from point A to B. Okay, okay, time is given. Time is given. It takes 2 seconds to move from A to B. Okay. They have given from here to here. This time taken is 2 seconds. Okay, then once we have got acceleration, I think we can use V equal to U plus 80. Na? I think that will be better. Instead of using this, we can use V equal to U plus 80. Okay. So V equal to U plus 80 we can use. Then it will be simplified now. Calculations will become simple now. Okay, so we got it now. V equal to U plus 80 we use and solve. V equal to V vector equal to U vector plus A vector into T. So final velocity is given there. Final velocity V, right? That is given as 12 by cap plus J cap minus 4K cap. Initial velocity, which is the velocity of A, we have to calculate. Acceleration, we have already calculated 4I cap minus J cap minus JK cap. Multiply time with this 2. So now I think we can solve it. So let us solve it. So VA factor we got it. 4 into 2 8 I cap minus 2J cap minus 6K cap. And bring this side, right? You have to subtract. So VA factor will become now this 12 minus 8 4I cap plus 1 minus 1 will become plus 2 plus 3 J cap minus 4 plus 6 plus 2 J cap. Yes, this is the answer of velocity at A. Yes, this is velocity of A. We can calculate magnitude if we want, but they are asking vector only, so we got this. Now position vector displacement. Displacement how to calculate vector. That we need to think about it, how to calculate. UT plus half it. Yeah, we can get this also. UT plus half it is for apply now. So displacement is equal to UT plus half A T square. Now solve it. Displacement means position of B minus position of A, right? That is what it is. And U vector we have calculated. U vector means velocity of A. So velocity of A vector into T. T is 2 here, right? T is 2 plus half acceleration vector into T square. Okay. So now we can calculate. So velocity of A into 2 U2. So 4 into 2 8 I cap. 3 into 2 6 J cap. 2 into 2 4 K cap. Plus half acceleration vector is 4 I cap minus J cap minus 3 K cap into t square. T square means 2 square it is. So now you solve this. 2 will get cancelled. So open out this 4 into 2, 8, 8 plus 8, 16 I cap it will become. And here minus 2, 6 minus 2, 4 j cap. And this is minus 6 plus 4 minus 2 j cap. Okay. So RB minus RA we got. RB they have given, I think in the question RB they have given. What is RB? 15 minus 7 minus 6, right? 15 minus 7 minus 6 minus RA cap. Now you calculated RA cap. Yes. You bring this side you bring. So 15 minus 16 minus I cap minus 7 minus 4 minus 11 j cap minus 6 plus 2 minus 4 j cap. This is the answer for R A vector, position vector we calculated. Okay. Yeah, so position vector calculated, this also calculated. Then work done by the force we need to calculate. Which force? That force. Now we can calculate, no? Because you know initial and final position. So we know the displacement also. Correct. This is the displacement, right? I think this is what is displacement delta r vector. So we have already calculated displacement. Then work done by that force is that force vector dot displacement vector. That force vector they have given in the question. This force vector, this one. 12 minus 3 plus 21. 12 minus 3 plus 21. Take that. This is the force vector. Dot displacement is this minus I cap minus 11 j cap minus 4 j cap. Work done by this force we can calculate. So 12 minus this, so minus 12 minus 1 is plus 33 plus into minus minus 4 into 4 into 84. So now we can calculate this. Okay. So 33 minus 6 96. This you calculate. This 3 9 to 60 minus 63. Clear? Yeah, that information was given. That's why we did not solve it. Yeah. Clear? So some portion can be completed when they do it. Yes, yes, we have to use integration. It is given here, now you see here. 12 minus 3, 21. Everything is constant. If it is variable means let's say it is in terms of t or in terms of x, y, z, then it will be variable and it will be integration you have to do. That is done. So with this we can wind up this today's session. Right. So anybody any doubt is there you can ask. Okay, then we will see. Right. Next class we'll see. Okay, bye bye. Yeah. Yeah. So hi Sam, how are you doing? Hmm. Just give me 1 second. What about your class? How much they have covered? Semiconductor did they start? Did, okay. Hmm. So, any doubts you have? What about anybody else in grade 12? Nobody is coming. Okay, okay. Anyway, but most of them are not serious, I think. Like you are serious and sincere. Little bit you are right. Otherwise, he will not come. So you have some sincerity, right? So generally, people are thinking that it is a free class. It doesn't matter, huh? Because whether it's come or not come, what difference it will make? That's what free things. They don't have any value, right? Because when you do things free, it doesn't have value. But when people will pay, suppose people are paying 10,000, 20,000, then they have to come, right? There is no choice for them. So that is the thing. Like that they are doing. What they can do? Free, free service, nobody appreciates. Hmm. Hmm. Ah, that is also a good book. Study that. Other lessons.